Hello everyone. So today we're going to continue on, or actually today we're going to start on chapter 13. So chapter 13 is the main chapter in talking about how to solve a system of differential equation. So we learn elimination method from chapter 12, which is a very basic technique that's kind of like what we go fall back to if we cannot do it any other way. But of course, the algebra involved in solving a very complex system using elimination method is actually very difficult to do. So what we're going to try to do is try to come up with some more clever way to do it. So one of the ways to do that is, as the title suggests, using what we call eigenvalue and eigenvector. So let's talk about how that works. So we call that when you're given a differential equation x squared equal to vector x, derivative of x equal to ax, where a is, let's say, some kind of constant. We know that the solution is actually in this form. Is in its solution is in the form of x equal to c e to the at. Now, how do I know that? Well, simple, because x prime equal to ax, meaning x prime minus ax equal to 0. Therefore, I can now define the differential operator to be d minus a of x equal to 0, which result in a characteristic equation r minus a equal to 0. Would therefore know that the characteristic root is a. Also, if you think about it, if x equal to c e to ax, then x prime would equal to c a e to ax, at, I'm sorry, and therefore x prime would just equal to a times x, which is a times c e to at, which is c a e to the at, which, as you can see, that's exactly what c prime is supposed to be. All right. So we know that that's the solution, and this solution right here is often referred to as an exponential solution. So x equal to c e to at is often called an exponential solution. And it's not surprising to see that a differential equation of exponential solution, because exponential function is one of those weird functions that when you take the derivative, is actually kind of fall back to itself instead of changing into something else. Okay, exponential function e to the x is probably the only one of the very few function that we know when you take the derivative is just itself. So now comes the question: can we use that concept to help us solve a differential system of equation? Well, let's see. So a linear system in the form of d vector x over dt equal to a vector x can have exponential solution also. And once again, the idea here is that because exponential function, when you take the derivative itself, therefore give us a possibility that when I take the derivative, it's just equal to some kind of transformation of itself, which is vector x. So in here, what we can do is the following. We can try an exponential equation. So therefore, imagine the following. We have d vector x over dt equal to a vector x with, let's say, vector x is x1, x2, to xn. And then d vector x over dt is actually dx1 over dt, dx2 over dt, to dxn over dt. And then, of course, we have our matrix A, which is kind of like our coefficient matrix. So in this case, I'm going to leave the coefficient matrix as a constant matrix. So A is a n by n constant matrix. So we don't want it to be any kind of function yet. We just want it to be a constant matrix. Now what we can do is we can try this kind of solution. We can try a solution, or maybe try solutions in the form of vector x is equal to e to the lambda t vector u. So therefore, it's basically a vector u multiplied by e to the lambda t as a coefficient of the vector. In this case, where u, vector u, is a constant vector, and lambda is a constant. So now interesting thing is, how do I know a solution in this form will satisfy the differential equation? Well, simple. Let's find out. So to show that it satisfies the differential equation, all I have to do is show that this equation is true if x is this. So the question is this statement true when vector x is equal to e to the lambda t vector u? Or rather, what condition of lambda and vector u will make this statement true? So let's find out. So if x is indeed that, so d vector x over dt would tend to equal to d over dt of e to the lambda x vector u. So since vector u is a constant vector, and we'll pull that out of the differentiation and just simply differentiate e to the lambda t, which come out to be lambda e to the lambda t vector u. And on the other hand, a vector x will simply just be a times e to the lambda t vector u. So if I claim that these two things are the same, then what happened is, if d vector x over dt equal to a vector x, then therefore imply that lambda e to the lambda t vector u must equal to a e to the lambda t vector u. And since e to the lambda t has to be a positive constant, I'm going to divide both sides by that. And when I do that, I come up to be something extremely interesting. That implied that lambda u vector u must equal to a vector u. So therefore, this is the condition needed for x equal to e to the lambda t vector u to be a solution. Solution to the equation d vector x over dt equal to a vector x. So that implies that if I can find lambda and vector u that satisfy this condition, I can then use them to form this solution. Vector x equal to e lambda t vector u, and that would satisfy our differential equation. Now, if you are looking at this expression that I boxed in and say, wait a minute, I kind of see something like this before. Yes, you have. You actually have seen it in chapter 3. See, the idea here is that if you look at this statement right here, consider the following. Look at lambda vector u equal to a vector u. Notice that this is satisfied. This is true if vector u is equal to the 0 vector. Now, however, if that is the case, is vector u is equal to 0, then our vector x equal to e to the lambda t times vector u will be e to the lambda t times 0 vector, which has become the 0 vector. And it shouldn't come as a surprise that 0 vector will satisfy our equation, because if you take the derivative, and that would just be equal to the 0 vector, which is clearly what A times 0 vector would equal to. So in this case, the solution vector x equal to 0 vector is called a trivial solution. Meaning that it kind of always works, and it doesn't really give us anything. Okay? Because we kind of know that it will work regardless. It's a trivial solution. So what happens if u is not 0? Well, if u is not 0, then we now actually have a solution. But in this case, what does that mean is this. It means that lambda and vector u are corresponding eigenvector and eigenvalue for the matrix A. So therefore, if we can actually figure out the eigenvalue and eigenvector for A, then those would satisfy this statement right here, the one in box, and therefore allow us to actually form our solution. So that's pretty interesting, because we know how to find eigenvalue and eigenvector, provided that we have a n by n matrix. So that's a very important revelation. So to demonstrate that process, let's show you an example. Let's say we have this system. Okay, which basically is equal to this. Okay, so that's the system in regular system form, and then that's also in matrix form. So let's try to solve this. So what I want to do is kind of understand how the solution look like. So what I'm going to do is, let's try to solve it using what we call elimination method first. So let's go ahead and do this. It shouldn't be too hard. So if I'm looking at this, I'm going to actually use the differential equation, the system form, to do it. So remember, what we're going to do is, I'm going to say this is x prime equal to x plus y. Therefore become x prime minus x minus y equal to 0. And therefore become d minus 1 of x minus y equal to 0. And we'll take the second equation, dy over dt, which is equal to 4x plus y. I'm going to say that means y prime equal to 4x plus y. That means negative 4x plus y prime minus y equal to 0. Therefore become negative 4x plus d minus 1 of y equal to 0. Good so far? So now what I'm going to try to do is try to eliminate. So what I'm going to do is, I'm going to actually, I'm going to get rid of the y. Okay. Yeah, let's get rid of the y. We can probably get rid of the y. Let's get rid of the y. So I'm going to multiply the first equation by d minus 1. And multiply the second one by nothing. So the first one becomes d minus 1 square of x minus d minus 1 of y equal to 0. The second one stays the same, negative 4x plus d minus 1 of y equal to 0. I'm going to add this together. These two things cancel out. And now I have this one equation, d minus 1 square x minus 4x equal to 0. Lucky for us, it is a homogeneous equation. So that makes it easier to solve the system. So therefore it becomes d squared minus 2d plus 1 minus plus x plus 1 minus 4 of x equal to 0. And therefore become d squared minus 2d minus 3 of x equal to 0. And if you think about it, then the two characteristic group would have to be 3 and negative 1. That's pretty straightforward. So therefore, tell me that x of t should equal to c1 e to the 3t plus c2 e to the negative t. And so now I can try to find y. So it's pretty easy to find y because we do know that dx over dt equal to x plus y, imply that y is equal to dx over dt minus x. So if I do take the derivative, it will be 3c1 e to 3x minus c2 e to negative t minus x will become minus c1 e to 3t minus c2 e to negative t. So remember there are only two terms here. So c1 e to 3t, you have 3 minus 1, so 2 c1 e to 3t. And then minus c2 e to negative t minus another c2. So therefore it's minus 2 c2 e to negative t. So therefore now we have our answer. We have this. We have this. So now let's write our answer. Our answer will be xy equal to c1 e to 3t multiplied by 1, 2 plus c2 e to negative t multiplied by 1, negative 2. So that's our answer. Now, notice that the answer is written as e to some power t multiplied by a vector. So obviously in this case, the number 3 is our lambda, 1, 2 is our vector u, and we have two pairs of them. Okay, and it shouldn't be a surprise that we have two pairs of them. Now, I'll show you what happened if I now want to do this entire problem, but using eigenvalue and eigenvector. So let's say we're going to let A equal to the matrix 1, 1, 4, 1. I'm going to ask you to find the eigenvalue and also the eigenvector for A. So hopefully you remember what to do with the eigenvalue and eigenvector, how to find them from chapter 3. So the way to find the eigenvalue and eigenvector is to form the determinant of A minus lambda I, and that has to equal to 0 value to guarantee that we don't have a unique solution to a homogeneous system. Because the unique solution to a homogeneous system is the 0 vector, which we don't want, because the 0 vector only generates what we call the trivial solution. So that would mean that the determinant of 1 minus lambda, 1, 4, 1 minus lambda is equal to 0. So if I find this determinant, that will be 1 minus lambda times 1 minus lambda minus 4 times 1 equal to 0. That forms the equation lambda squared minus 2 lambda minus 3 equal to 0. Some of you might already have a little deja vu because it seems like we see this trinomial before. Oh yeah, of course we have. It's right here. See that trinomial? Yep. See, the idea is that this equation, if you recall from chapter 3, this equation has a name. It's also referred to as characteristic equation. It's not by surprise that it's called characteristic equation, because it is the same exact equation that we wind up having here. Okay? And yes, for most problems, it should almost always wind up being the same because of the connection with the eigenvalue and the solution of the characteristic root. So, Here will give us two different lambda value. Lambda 1 equal to 3 and lambda 2 equal to -1. So for lambda 1 equal to 3, we can now form our matrix, which is 1 minus 3, 1, 4, 1 minus 3. And then if I multiply that to any vector, uv, I need to get the 0 vector. So if I look at this, that just becomes -2, 1, 4, -2 of uv equal to 0, 0. So remember, if you do it correctly, you have a matrix that's singular, meaning that you can actually reduce to a matrix with an entire row equal to 0. Which in this case shouldn't be too hard for you to see that the top row is a multiple of the bottom row. So here I can just simply look at the equation -2u plus v equal to 0 to try to figure out what is the solution to that. And it seemed to me that I can say uv just simply equal to, I don't know, 1, 2. That will work. And so therefore we have our vector u1, which is 1, 2. And at this point, I would strongly recommend that you pause the video and try to find the second eigenvector on your own. I'm going to continue, but you really should try to do that on your own. So 1 minus -1, 1, 4, 1 minus -1 times uv equal to 0, 0. So therefore it's 2, 1, 4, 2 uv equal to 0, 0. That result in the equation 2u plus v equal to 0. Therefore, you can say that uv must be 1, -2. Because if you plug in 1, -2 into u and v, it will satisfy the equation. Now, here sometimes you're often confused because, but can it be something else? Absolutely. Remember, when you have an eigenvalue and eigenvector, any multiple of the same eigenvector will be okay to correspond with the same eigenvalue. So the uv that I choose are simply just what I think is the simplest one. If I look at the equation 2u plus v equal to 0, you could definitely use something weird. Okay, you can do 1/2 and -1. That will work. Or anything in the multiple of 1 and -2 would work. Like 3, -6 would work. And so on and so forth. So I'm just going to pick the easiest one that I notice. And now here comes the revelation. If I now compare our solution, which is xy equal to c1 e to 3t times 1, 2 plus c2 e to -t times 1, -2, notice that the eigenvalue lambda 1 is right here. The eigenvector 1, 2 is right here. The eigenvalue lambda 2 is right here. And the eigenvector is right here. Implying that our solution actually takes in this form. C1 e to lambda 1t multiplied by vector u1 plus C2 e to lambda 2t multiplied by lambda vector u2. And that creates a possible way to generate the solution to a system of differential equation, which is summarized in this right here. So therefore, the method of solving a system of constant coefficient, we do need the matrix to be a constant matrix, linear differential equation, by using eigenvalues and eigenvector of n dimension. Oh, actually, you know what? Maybe I'll write it this way. Yeah, sorry. I probably should mention the dimension before I say using eigenvalue, eigenvector. So the method of solving a system of constant coefficient linear differential equation of dimension n with eigenvalue and eigenvector can be summarized as follows. Okay? Oh, I'm missing a Z right here. There you go, missing the Z. Can be summarized as follow. So, first, we're going to have to find the eigenvalue. Oh wait, actually, you know what? Let's start with the following. Let's say we're given d vector x over dt equal to a vector x. So that's our system of constant coefficient linear differential equations of dimension n. So therefore, in this case, A is n by n constant matrix. So first step is to find the eigenvalue of A using the equation, the determinant of A minus lambda I is equal to 0. So that's a typical process to find eigenvalue that you learn in chapter 3. Number 2, for each eigenvalue, let's say lambda k, find the corresponding eigenvector. So now the eigenvector is actually not unique, so you could have multiple of different eigenvalue that will work, but once again it doesn't really matter because of the presence of C1 that you can actually change that. So therefore you just have to find an eigenvector. It doesn't matter which one it is. So eigenvector vector u sub k by solving the equation A minus lambda I, A minus lambda k I times vector u sub k is equal to the 0 vector. And that is basically what we did right here in solving this two thing right there. And remember, you should have a multiple solution because the idea is that this system right here is actually have an infinite solution which takes the form of a line. So you're basically just been looking for the direction of the line, the direction vector of the line, which can be any multiple of the same direction. Once you have that, then what happened is the following. So now this is an interesting step. If the solution e to the lambda 1t vector u1, e to the lambda 2t vector u2, dot 2, e to the lambda sub kt vector u sub n are linearly independent. Notice that you will get n that many eigenvector because the matrix A is n by n. Now, however, the important part is the following. Even though you are guaranteed to find n that many eigenvector with that many corresponding n that many eigenvalue with the corresponding n that many eigenvector, The problem is some of them might be repeats. So meaning, in this case, when I say that if the solution listed here are linear independent, meaning all the lambda value are distinct. Maybe I should write that out instead. Meaning that all the eigenvalues are distinct. There's no repeated eigenvalue. Then the general solution to this system will be in this form. Vector x of t is equal to c1 e to the lambda 1t vector u1 plus c2 e to the lambda 2t vector u2 plus dot 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 plus c sub n e to the lambda sub nt vector u sub n. So that's how the solution to our system will look like. Now, if you think about it, that actually kind of similar to the way a regular single equation look like, in the sense that we don't have lambda, but we do have the characteristic root r1, r2, and so on and so forth. And also because you have a system of equation, your solution is by itself, whole bunch of equation also, then there is a vector u1, u2, and un to kind of show the proportion between each equation or each solution. So that's how that works out. Now, unfortunately, my time right now, the video is about 32 minutes already. So I'm going to stop right here. And we'll continue from this point on in the next video. All right? Talk to you guys soon. Bye-bye.